So we're doing the test in here on Monday, but that also wants me to cover what happened with engineering mechanics. So it was a little bit, because we all know that Ed's over in Enid. And the way they set it up, because the time that I have for Ed's space to work on things, and the time that we have for you guys' space are two different times. We have two different classes that are in Blackboard. Well, that doesn't make a whole lot of sense, because that means I have to do all the same work in Blackboard for one. So I asked Bobby to do a master. Not thinking about it, I said, well, we're early in the semester, no big deal. Not thinking about it. She wanted me to go to keep one alive, and I didn't think about it. And so what happened was we wiped everything out. So I had to start rebuilding, which is okay, because it's, I had the other class. But that meant all the edits that I had done for the trusses also disappeared, because I didn't realize that I had done that much editing, which I had. And I was like, okay, well, that's what happened. So what happened is you now have a master class, like we have a master class for statics, we have a master class for a bunch of them. So you now have a master class. And so I didn't put all the gory details in for the trusses that was there before. Make sure your truss can span 24 centimeters. That part's the same. I did get you a link to the common trusses, so it's a really good page that's got the link to the common truss. Everybody is responsible for building 3 trusses. So everybody's going to be responsible for building 3 trusses. We are breaking them here in Tonkawa on Monday. We'll break them in Enid a week from Friday, so that's February 7th. We'll break them in there, so I'll break Ed's over there. And then we've got that stuff straight. The report for, which you already turned in, you were early bird, yours is already there. The report for the cable problem is on this Friday. At 5, and there is a spot in Blackboard to submit it, but you don't have to do it, I got yours, so. And if there's a problem with submittal there, then the report for the trusses will be February 14th. And then we'll start the bridges. And those of you who weren't there for the discussion, bridges are going to be made out of linguine noodles. I'm going to play with it a little bit. It's going to have a mass limit. Okay, it'll have a mass limit, and then and then we do have a width limit, because we're going to use the same tester, the bridge tester that we're using for the trusses. We just won't use the truss. So I've got to work out the dimensions for width on the bridge. But so there'll be a mass limit and a width limit on the bridge. But I'm thinking our mass limit is going to be enough that you guys can do some pretty cool things with linguine noodles. And I'll buy over the weekend. I'll buy a big bag of linguine noodles. There you go. Well, I don't know. Nothing says it has to be made from dry linguine noodles. But it does have to be structurally sound. Okay. It does have to be structurally sound. Well, no, you may want to do something with a wet noodle. That we do it and shape it. Mm-hmm. That's why I'm thinking this noodle thing was a great idea. I think this noodle thing's a great idea.
I'm a little sad about the weight limit.
No, you have to do something, because you can. I do not want you building just a composite beam. Mm-hmm. Yes, that's why there will be a weight limit. That's why there will be a weight limit.
We were talking about it the other day. We're like, well, why don't you just cast a mold in resin and put one of your...
That's why we're having a weight limit. All right, so let's go to this, and on Friday for you two, bring some photocopy paper to do, because you're gonna be doing I'll be in Enid, and I will bring some photocopy paper, make sure you have a Sharpie marker.
Okay.
Yeah, because if you try to do it in, this is what happens to you guys, if you do it in pen,
Super skinny.
you can't, and I won't be here. Usually I would just give you mine, I won't be here, so, so it's a Sharpie marker and photocopy paper, and you'll want, so you see what happens if you don't have a second sheet of paper under, so you want to have, you know, a little bit of a stack of photocopy paper,
Okay.
okay? Friday, they're presenting problems. They're actually gonna present the problem, so I'm giving you some tips on how to do that. So we're doing section 2.9. Okay, and we're talking about the dot product of our vectors. And this is our scalar product, okay? That's our scalar product. Now, you guys all remember that scalar products and and vector products are going to have different rules associated with them. So this is our math review on this kind of stuff. In a scalar product, A dot B is equal to B dot A. And we all remember that this is what's tricky when we get to cross products. Because what they call it, the commutative law, does not apply at cross products. It does apply for dot products, not for cross products. And then I can have any kind of little scalar. I could do that. This can be this times this dotted with B, or this can be A dotted with AB. Yeah, same thing. So a scalar can do whatever. And I can do a dot product So those are my rules for scalar products. Pretty straightforward, we can play with them. Now, things we have to remember, right? Things we have to remember is I dot I equals 1. I dot J equals 0. I dot K equals 0. So this is just J dot I, that equals 0. J dot J equals 1. And J dot K equals 0. And then I get K dot I equals 0. K dot J equals 0. And K dot K equals 0. And that's just a function of our dot products. So things that are going to be in the same plane are actually going to come together. Because what that all does,
Wait,
So
K.
K dot K.
oh, it's 1. Sorry. Yeah. At least you're making me honest. Yay! So if I have the gory details, the whole gory detail thing, I get A dot B, which is going to be AXI plus AYJ plus AZK, dotted with BXI plus ABYJ plus BZK. This gives me AXBXI dot I plus AXBY I dot j plus ax bz. Yes, this is going to be a long one, guys. I dot k. Then we do the second row. We get a y b x. This is j dot I plus a y b y j dot j. Put my little brackets there. Plus a y b z j dot k. Then we do the last one. So we got all those. So we could have 9 terms. Lucky for us, that all go away. And so we get ax bx 1 plus ay by 1 plus az bz 1. So if we go to our vector notation, we can go in and we can totally eliminate all that lovely cookie stuff. Everybody good with that? Totally gory details, all that part. But what's important to us goes back to this a dot b is equal to ab cosine of my angle. And what that's saying is this. I have a vector A and I have a vector B. And I've got this angle there. That when I put these things together, I'm going to be able to look at my new direction. So the picture that the book gives us is like this. This is my U of B, and this is my guy wire U of R. Here's my angle. And I can determine the angle of the rope by doing UB dot UR, because we now know that that's 1 cosine of my angle. And the angle can actually end up being the cosine inverse of A dot B. The magnitude of AB gives me my angle. So if I know my unit vector here, and I know my unit vector there, I can figure out the cosine of the angle between the two. Which leads us to something that we already know and we've already been dealing with. That if I have a vector, here's my vector A, and we know that angle. This is the projection on this side, or on whatever axis this is. We'll give this axis little u. So A along u is A cosine theta u to get us on our vector here. And then this gives us our perpendicular part as well. So we did a couple problems where we were doing those weird, that hey, this Cartesian coordinate system wasn't going to work for us, and we wanted to look at the projection of that vector on another part. That's what we do. So it's very similar to what we've been looking at. And it's looking at, so that we can give ourselves a vector or the magnitude of something on any dot product between a unit vector along the direction and whatever force vector we have. So we can get those various component parts to it. So we've actually kind of been doing it all through this section. But we really hadn't kind of dived into it. Let's see if I want to do this one. Oh, yeah, this is exactly the type of problem that we're gonna get. All right, so I'm gonna give you a minute to draw the problem. And what we wanna do with this problem is find the angle between this vector and that vector. Okay, we wanna find the angle between these two vectors, is what we're gonna do. So I'm gonna give you a second to draw your picture.
What did this homework do last night?
I think so. But it's not something you hadn't seen before. That's why I didn't worry about it so much. Was it last night or was it due tonight? Today's the 29th.
It was
Just
due
do
last
last
night.
night.
Was it due last night? That's so you could have the adaptive stuff done. There's Ed. Yeah, so give me a second to draw the picture. I gotta draw the picture too. And we're getting kind of in a spot there where we can kind of get going. Okay, so the first thing I gotta do is find a unit vector along F1. Oops, I wrote 25 pounds, that's 30 pounds, we'll get there. But I don't have to worry about the actual magnitude for this part, because all we're doing here is we're finding the angle between those axes. So luckily for us, they kind of give us some information. So I'm gonna do the unit along F1. If I'm doing, so this plane here is in the XY plane. Okay, so this plane here is in the XY plane. So I'm gonna get the cosine of 30 degrees there. This one down here is in the is from the XY plane down. So it's gonna give me that sine of 30 degrees. If I go back and I look at how we dealt with a few things before, and now I can do this, this is the cosine of 30 degrees. Cosine of 30 degrees for the J direction. And then it's minus the sine 30 degrees for the K direction. So for this vector, we got 30 to 30s all there. Now this vector is giving it to us kind of in our other aspect of it. So let's, if I do this one, so the unit vector F2 is going to be, trying to see it, all of a sudden I'm not seeing it. Oh, if I do it in terms of alpha, beta, gamma, and they gave me this one, they give me this one, I can get the other one, and I get cosine of 135 in the I direction, plus cosine of 60 in the J direction, plus cosine of 60 in the K direction. And if I write those out, so U of F1 is equal to 0.433 I, actually 0.4330. 0.433 I plus 0.75 J minus 0.5 K. U of F2 is equal to minus 0.707 I plus 0.5 J plus 0.5 K. So now if I do UF1 dot UF2, I get 0.433 minus 0.707 plus 0.5 times 0.75 plus minus 0.5 plus 0.5. This ends up putting into the calculator, get minus 0.1812. And that means I can do that the angle is equal to cosine minus 1 of minus 0.1812. And that gives me 100 degrees. So we can use it to our advantage. And because it's so straightforward and simple, you're likely to see one of these on the test on Wednesday. No, Monday, sorry.
We're gonna see one of these on
Huh? One of these problems? Now, am I likely to give you a really complicated one? Not.
when you said likely to see one of these, and this is pretty complicated.
Okay, I'll give you a simple one. Let's do one. Let's do a simple one.
Have you gotten a chance to grade those quizzes?
No.
Yeah, I'm just dying to
Please
see
don't.
that. It's,
I'm hoping that, now that was, I'd like to have had them graded so that you could have them back, but I will not be on campus tomorrow. So if I get them graded in class, then, or by class time, I'll be able to have them handed out in class. Okay, so let's do let's do, I have a device. Oh, and we'll be nice. We'll make it a cannon that we can send off fireworks with. And I'm making this up right now. So you all know what happens with my numbers when I make things up, right?
That's perfect.
Yeah, right. And off the end of this cannon, I've got a tripod piece that's here, and I got a tripod piece that's here, right? So we're gonna be able to shoot this out.
Wouldn't that be a bipod?
Well, it's actually tripod. Right? 1, 2, 3. We've got 1, 2, 3.
Yeah,
right?
but that's only 2 legs.
Well, 1, 2, 3. Okay. So if I look at it from straight on, that's what we're doing here. I'm looking at it from straight on. Right? I'm looking at it. And for whatever reason, we put a scale on this one and we put a scale on that one. Put a scale on that one. And we want to know the angle between those. Okay? So we've got that part here, and when we look at, well, in 2 dimensions, it's going to be really easy, right? Because if I do this in 2 dimensions and I tell you that this is 60 degrees, and if I do this in this side and I tell you that this is 40 degrees, we know how to figure that out, right?
Yes.
We know how to figure that out, so we can't make it that simple. Okay, can't make it that simple. But we could do it this way, that this is in the XY plane. And we'll make this 40 degrees. And this one is going to be where this is going to be not in the XY plane, but we're going to set it. So we know that one, okay? I've got this so that we got this. We're going to set this. So if I do it this way, I'm drawing here. We're going to set it back from the X. This is the XY plane. We're going to set it back along a Z direction of -4. So this is going to be in the YZ plane. If I've got my picture drawn right. So this is in the YZ plane, this is in the YX plane, and we're going to go ahead and we're going to give this a size of 5 in terms of length, and we're going to give this a size of 5 in terms of length. So we got it kind of cockeyed, right? So I've got this one in the XYZ plane, I got this one over here. They both have the same length. No, I have that one that way. Okay? And we'll find the angle between them. So this one we got to find the U vector. So this is going to be vector 1. This will be vector 2. So the U vector for 1, we've got it length of 5 at a 40-degree angle. So this is going to be 5 cosine 40. And that's got to be minus because this is going to be in the negative direction. And the I direction, minus 5 sine 40 in the J direction. And I have no K direction on this one. U2, we say it's, in this case, we're -4 and we've got 5. So there is no X component in this one, so there's no I. My Y is, I have enough, yeah, if I'm in my plane like this, I'm making sure I have enough information. So this this is -4, that's 5. I've got 2 sides.
You can. Just, that can be a theorem, right?
Yep, should be. Should have a right angle. But this one is gonna be, so if we want, if I've got, this is gonna be 16. Hang on, 16. I've got a picture in my head here. Well, I'm like that. That's 4. This is the hypotenuse. Okay. 5 is the hypotenuse. This side's got to be 3. It's 3, 4, 5 triangle. But this side is the hypotenuse. That's what I was trying to figure out. Trying to picture it in my head. We want the 5 to be the hypotenuse. So we know the other side. If that's 4, we know the other side's got to be 3. And if I'm looking at my angle, so hang on. So I've got 3 down, 4 over. There we go. No, that didn't draw right. So I got 3 down, 4 over. Here's my hypotenuse, so I can keep track of what angle I'm working with. And this is the y direction, and that's the z direction. Trying to keep track, okay? Trying to keep track of the picture. So you can see where you get yourself when you're working these problems without thinking through them sometimes. Like I told you, things go bad when I make up a problem all at once.
So that would be underneath the y-axis.
Yeah.
Instead of, that's just for visualization.
Visualization, yeah. And that's just for, because basically what we've got are these 2 vectors. So we're going to use the points of my pen. I got a vector here and I got a vector here. And we're trying to find the angle between them. One's in the x, y plane and one's in the yz plane. So again, for visualization purposes, that's what we've got. And we know that the y, well, we know if this side is 5, this side is, and we told you that side was 4, that side had to be 3. Because it's 3, 4, 5 triangle. So I'm not even drawing my triangle very well. But that's what we've got. Because now if I want to do my j, and we're in negative j, so we got a negative, and we're in the negative k, so I got a negative, so I've got that part okay. And if that's the angle that I'm using for my j, if this is the angle I'm using, we know the hypotenuse is 5, and I've got to do the adjacent, so that's cosine, so there's my 3/5, which makes this one the 4/5. Now, this one's okay, I think. Now, the question we have is, are these going to end up being, this one 5 is the magnitude, so I don't want to do this because I just want a unit vector. So I just want to be in the cosine and the sine. These are just the cosines and the sines, so I'm in a unit vector. So does everybody see why I got rid of the 5? Because I want this to have a magnitude of 1. Now, I could have done it the other way, okay? I could have gone ahead and solved this, figured out the magnitude divided by the magnitude. Because remember, my r vector is, for, if my r vector, if I figure that out, that's what I actually wrote with the 5. Then my unit vector is going to be the r vector divided by the magnitude of the r vector. And in this case, I had a magnitude of 5. Because that's what I gave in the problem, that length was 5. These were the same length. So I could get rid of that 5. So, because I want the unit vector, I want that magnitude to be 1. So now, I've got u1 is equal to, everything's negative, cosine of 40, that's 0.766, got a negative in the I direction, minus sine of 40, 0.643 in the j direction. And I have u2, 3 divided by 5. This is negative 0.6. And I have 4 divided by 5, negative 0.8. Oh, this is a J, and that's a K. So if I dot product this, I only have negative 0.643, negative 0.6, because I don't have another corresponding I don't have another corresponding J. So I dot product that, and that's going to give me 0.3858 arc cosine of that. Gives me 67.3 degrees. If I'm using my pins here as my example in 2 dimensions, that gives me, so I'm trying to hold my pins here, that gives me this angle right here between those two. So that's also going to be the trick, because we thought we were going to make, when I first was drawing the problem, looked like I was going to give you this is the angle we'd end up calculating, but that's not. We ended up calculating this angle. Yeah.
I'm still confused why you got rid of the 5.
Okay, because when I first wrote this vector, the length of this vector was a 5. And so I wrote out that, so that actually was an R, not a U. U as a unit vector is going to have a magnitude of 1. There was no reason to multiply by the magnitude of that big vector when I was doing the unit vector.
Okay, so all unit vectors equal 1?
All unit vectors equal 1.
Okay.
Yeah, the magnitude of the unit vectors equal 1, because our force vectors, when we do our force vectors, it's going to be the magnitude of the force times whatever unit vector that we have. Yeah, so I just pulled the magnitude out.
So the unit vector is the same as like the R vector just minus the...
So my unit vector is my R vector divided by the magnitude of the R vector.
Okay.
So I really wrote the R vector, because that included the magnitude of how long my leg was.
Okay. But just to turn it into a U vector, you just take the...
Well, because I knew what the magnitude was, what I plugged in, that's why I pulled out the 5.
Okay.
Sometimes I won't know, okay? When you're figuring out your unit vector, sometimes you won't know.
So you'll just have to do the R divided
You have to
by...
do the R divided by the magnitude of R.
Okay.
Yeah, sometimes you won't know.
Okay.
Yeah. Like the one I'm about to do. Well, the one I'm about to set up, because it looks like we're running out of time. This is problem 108 and 109. It's the chandelier problem. It's a chandelier problem. So, in our chandelier problem, we've got a chandelier supported by 3 chains. And they're at point O. If the force in each chain is 60 pounds, so we know the force in each chain is 60 pounds, we can express each of these vectors in their Cartesian coordinate system. And then you can calculate the resultant force. So these become, what have I got? All right, these become, what have I got? And I can give myself, I know that this is why you sometimes don't know if you have a unit vector or not. So let's look at that first one, or look at this first one. So if I do f of c here, so I have f of c, we know that the magnitude of f of c is going to be 60 pounds. But let's get my vector here. My first vector is, this is in the z direction, and this is in the y direction, and I have no x. So there's 0x, so this is going to be an r vector along c, this part right here. It's going to be an r vector along c, so I've got 0 in the I direction. I'm going to call this minus 4 in the j direction. And I have minus 6 in the k direction. Now if I look at the magnitude of r, that's going to be 4 squared plus 6 squared, which is going to be 8 plus 36, which is the square root of 44.
4 squared is
4 squared.
Oh, 16, thank you. Things are, so I get 16 plus 36, that's 52. Under there's the square root is 52. Gives me 7.2. So the magnitude of that is 7.2, so I don't have a unit vector. So I've got to get my unit vector. So the unit vector along C is going to be minus 4 minus 6 divided by 7.2. So that's going to be 4 divided by 7.2 gives me a minus 0.556. Gives me a minus 0.833. So that's why I say sometimes you don't know the magnitude of that vector. So now my f of c vector, you multiply by 60, so this is going to be minus 50 K, because 0.833 times 60 turns out to be 50. And this is 33.3 J, and that's a minus. Because this is going down, and that's then going there. The way I'm interpreting it, this is the positive x direction. I'm interpreting that's the negative y direction. That could be the positive. If that's the positive y direction, then that becomes positive.
On the test, will there be distinguished positive and negative, or is it kind of just like that, how you interpret it?
If I don't give it to you, it's how you interpret it, and as long as you show your work, I'm going to give you credit for it. And what I would do on your picture is go ahead and tell me if you call that negative or positive. Now, the book actually called that positive.
Well, if we're looking at L, then it's positive. If we're looking at C, then it's negative.
And that's why I said, so it's a case of how you interpret it sometimes in the pictures. In this case, we were just trying to figure out an R vector. So it wasn't as critical, but in other problems it may be. And that's likely where you're gonna get crosswise with Pearson in some cases, is how you look at that vector. So first thing, that's another thing when you guys are working your homework. If you get crosswise and you think, well, I think I did it okay, look at your orientations. Did the book interpret it a little different? that's gonna help you out. All right, so you two are presenting on Friday. Yeah, your question, Brandon?
I love that